Okay, Article 242, Overvoltage Protection. This is a change in the 2020 National Electric Code, where we had two articles previously dealing with lightning arresters and surge protection devices. And both of these work on similar principles, and that is when there's an overvoltage, it's going to take some action to reduce that overvoltage event. Now, Article 242 deals, now it's combined those two articles into one. One part is going to be dealing with under 1,000 volt systems, or 1,000 volts and less, and the other part of that section, of that article, deals with over 1,000 volts. We're not going to be getting the over 1,000 volts. We're going to be talking about the systems that are 1,000 volts less. Article 242 provides general requirements, installation requirements, and connection requirements for overvoltage protection and overvoltage protected devices. My research department, I'm going to have a check right now. Research, do they use the word surge protection devices still in this article as it had been used in previous articles?
Yes.
Okay, so we're now going to switch from overvoltage protection devices. We have lightning arresters. Is that the proper term they're using? And then over 1,000 surge arresters, which is over 1,000 volts. And then we have surge protection devices. So we're going to focus on that. John, you're the one that's going to be driving most of this because, you know, you really understand this more than. Let's talk about voltage strikes. Let me read the text, set it all up. Voltage spikes and transients, and talk about speed. Voltage spikes, transients caused by switching of utility power lines, power factor correction, capacitors, or lightning can be reached thousands of volts in amperes. So the outside, utility, lightning, talk to me about this. How does this affect us once we get into building? What's going on here?
Sure. Well, essentially, lightning or switching transients on the utility can corrupt the sinusoidal voltage waveform, and it can cause very large spikes, just like it sounds. It's a very large overvoltage. So if you've got 120 volts RMS, you could have thousands of volts on top of that for a very, very, very short period of time, microseconds.
So we see the little image right here, and I'll kind of zoom in on here. Clearly, even if it doesn't strike the power line,
correct,
there's this amazing electromagnetic field, and that magnetic field cuts into the conductors, Jacob. You follow, because you're a student in our class here, and that induces a voltage. Now, the utility obviously has lots of systems to try to get that energy to the earth, because that's where that energy is trying to go to.
Yes, exactly. Yeah, lightning events are trying to get to the earth, unlike
we'll stop right there.
Okay.
But lightning events, and the utility is outside, and they're trying to deal with these lightning events, that causes this very fast, very high amount of energy, high voltage, and then that, no matter what they do, that energy, a part of that is going to be transferred from the primary of their system over to the secondary winding.
Yes, it affects the entire system.
Yeah, I mean, because the primary voltage is transformed into the secondary voltage, Jacob, and if there's this momentary millions of volts striking in the primary, or hundreds of thousands of volts, well, that's still part of the primary winding, and then it's going to just spike something on the secondary. Okay?
Mm-hmm.
All right, so now, let me read this. Oh, Eric, did you want to say anything at all on that? Okay. Now, voltage spikes. Voltage spikes down the bottom are called transients, are produced by premises equipment, photocopiers, laser printers, other high reactive loads cycling off can be in the hundreds of volts. What does it mean by, if you can, reactive loads? And what are the kind of loads? And what does this mean that inside of a building, I'm now putting spikes, transient spikes?
Sure. Well, when we're talking about reactance, if we're talking about inductance, if you're instantaneously trying to interrupt the current flow through an inductor, inductors resist the change in current. So if you're trying to interrupt the flow through an inductor very fast, you're going to have a very large voltage spike.
Give me an example of that.
Well, on old automobiles, the distributor.
No, I mean, in a building, what would be an inductor that would turn off quickly that would cause the spike?
Oh, there's lots of things. So a motor is one example. So you're trying to interrupt the current flow through a motor. very fast. If you could see,
turn it off.
Yeah, it just
Turn it off.
Yeah, just interrupt the current flow. Turn it off. It still spins, but if you're just trying to interrupt the current flow very fast, if you can watch between the contacts, there's going to be an arc, and there's a high voltage transient associated with
So
that.
anything that has a large inductive load, air conditioners, right?
Sure.
Inductive loads, and you cut it off. Jacob, electrons are flowing, right? And they're going back and forth in our fundamentals course, and all of a sudden they're moving, okay? And then all of a sudden it's interrupted, okay? And then it's closed, right? I mean, it stops. Well, when it stops, it kind of like the water hitting something, and it just for a second, it just kind of goes high. It just makes it a little. But now you still have the 60 volts, everything, but then you have some loads that are turning off. It's just like if a load turns on, what do you think happens to the voltage? Here's the sinusoid. What happens, do you think, with the voltage when the load turns off? I mean, when the load turns on. Well, it makes a little dip. Because when it first comes on, that a motor or lock rotor current, right, 6 times it starts, well, there's a little dip. Well, when it turns off, then guess what? Well, now it's inductance and it's a change in current. Well, then it makes it a little quick pop. Does that make a little sense? And those that don't know this, Jacob is a student in the class, so he's 17 years old, and we're trying to help him understand the fundamentals. Am I about what we said there, John, right?
Correct.
So load's turning off, and when they turn on, it dips. When they turn off, they can spike.
Correct.
Okay, no big deal there. So now, let me just set this up. Let's just assume that the utility has some kind of spike, or somehow we have 6,000 volts of transient spike on the primary. Well, since there's some kind of turns ratio between the primary and secondary, let's assume that whatever that ratio is going to be, that I end up getting 1,000 volts on the secondary, because it's going to transfer from the primary on conductors, because we're not talking outside of a building, we're talking about inside of a building. Well, then it's 1,000 volts. Well, then you end up getting 1,000 volts right to the load. And these loads could be computers, electronic equipment, and then, you got what? You got dryers with all kinds of controls on there. You got refrigerators with TVs on there. What other type of loads, guys, that we have in a house or in a building that are electronic sensitive? All your everything. It's computers. Everything is sensitive.
Audio equipment. Network equipment.
Network, you're right.
Intercom systems.
Well, short version, there's a law of Murphy's Law without getting into all the details, but pretty much if you're going to destroy anything, you're going to destroy which one?
The most expensive
The
thing.
most expensive.
Yeah.
I can get into the law, but Jacob, we don't have the time to get into that law. But you're going to destroy the most expensive thing. And it would be the thing that would be, now the most expensive thing, just so you know, will always protect the least expensive thing. So it will sacrifice itself to not hurt something that costs nothing almost, okay? So now that we know that transients, because of that energy going inside there, it's only supposed to be rated 120. They didn't plan on having it more than that. Now you get 1,000 volts. So now, they get something, what is called a surge protection device. Now, Jacob, let me explain it a little bit, and then John's going to get a little bit more inside here. You have this transient, and you have 1,000 volts coming in here, right? 1,000 volts? But there are rules on parallel circuits. Imagine that I put something here, and I put a resistor here. And I put a resistor here with really, really low resistance, almost to the point that it's a short circuit. Now you say semiconductor, that could be off, it's an insulator, and then at a certain voltage, what is it, John, 330 volts?
Mm-hmm. Well, yeah, there's different classes, but yeah, for example, 330
Okay,
volt.
so if you go over 330 volts, this device right here becomes a conductor, a dead short, let's just say. Well, if you make a dead short right here, what's going to happen to the current flow traveling between these 2 points right here? If this has a really low impedance, it's a short circuit effectively. Is the current going to get higher? I is equal to E over R. So now what's going to happen is, if you create this high amount of current, now you're going to have a large voltage drop because it's high current. Okay, so this resistor would be here, and we can do a calculation on a series circuit and come to find out that if we can make this so that this resistance is so low, that would cause the voltage drop to be so great. Now, loads are connected in parallel with the surge protection device. And we want this thing to get so low, to create so much current, to create so much voltage drop, that the load connected in parallel, rated 120, would be able to be protected by a device that will only, it would only turn on if it's over 330 volts peak, not RMS. Now, here's what's going to happen. If you do that, will there be a lot of heat? Yeah. So these devices, they're called surge protection devices, are designed to shunt the current, they call it, or to clamp the voltage. We want to clamp it at 330. We want to shunt it so that we don't go over 330. These are some terms that get used, okay? But the thing's going to get hot. Okay, John, want to talk about that, about the heat, and what do we do with that? I mean, how does this, anything else you want to say about that?
Sure.
The testing, anything?
Yes, it's a very fast event, so it is conducting thousands of amps sometimes, but it's such a fast event typically that the heat is able to be managed inside the device. If it's a slower event or a longer event, then there are certain circumstances where the heat can't be managed. So there's different ratings of the surge protectors. You'll have a joule rating and maybe an ampere rating also. You've got to be aware to match the rating of the device with the potential hazard. So you can have an overvoltage that can completely destroy a surge protector just because it's trying to conduct so much current, it blows up, it destroys itself. And you definitely want to stay away from that. So the way, like you said, the way the surge protector is working is it's conducting current. It's essentially short-circuiting, in this case, the ungrounded to the neutral. And the voltage drop, it's flowing a lot of current, so the voltage drop, the question is where's the voltage going? Because you've got 1,000 volts coming in, but you don't want your load to see 1,000 volts. Where's the voltage going? You're flowing a lot of current, essentially in a direct short. You're dropping that voltage across the impedance of the line and the transformer.
Let me explain that to Jacob. Jacob, this is a series circuit. On a series circuit, Kirchhoff's law says that the voltage drop of all the resistors in the circuit will equal the voltage source. So if this is a 120 volt circuit, and if I have some kind of conductor here, but it has resistance, okay, then it's going to be a resistor. You have a conductor that has resistance, you have this surge protection device with resistance, and you have the conductor with resistance, and you're going to carry thousands of amperes. Then it's going to cause the voltage drop in this device right here to be significant. And that's where the heat is going to take place right there. So where's the voltage go? Well, it's a series circuit. This might end up being 100 volts on the wire or 200 volts on the wire, you know.
Or 800 volts.
Or 800 volts on this wire, 800 volts on this wire, and this device here, let's make it easy, 1,000. Let's just say that if there's 1,000, let's say there's a 100 volt drop across the wire carrying whatever thousands of amps, and a 100 volt drop across this wire carrying whatever 1,000 volts. So that's going to get me down to 800, but I need to get down to 330, and then this is going to be, let's say, 470 volt drop across this. So the voltage isn't going anywhere, it's just being distributed.
Yeah, the voltage drop across the device is going to be the same voltage drop that's across the load.
Right, watch this. If this voltage, oh, you're right. Okay,
So
okay.
that's good.
If this is 330, then this is 330.
That should be 330
minus
too.
from 1,000, that gives me 670.
Yeah.
Let's say two wires the same length, 670 by that, it's going to be 360. 73, whatever. What's 670 divided by 2?
335.
But here's what happens. You're probably right, but I've learned that you never do it in your head. So it's 1,000 minus 330 equals divided by, the 6, okay, equal. Oops. You don't divide it by 3. 1,000 minus 330 divided by 2, okay, it's not 837. 1,000 minus 330 divided by 2, okay.
335.
I keep
335.
keep getting 837. So it's what?
Let's try 335.
Okay, so that's a 335 voltage drop. That's a 330 voltage drop. That's a 335 voltage drop. Well then, and they're in parallel. So now resistors in parallel are the same. Right? So that's how it works. This is not complicated.
Right.
What's important about this is there's a lot of people out there making this statement. Jacob, you're going to hear this. Well, you have to have a good ground for a surge protection device to work. But take a look at this graphic here. There's the current leaving and returning back to the source. It has the voltage drop and it's in parallel, so that's 330. We're going to clamp it at that. Well, then that's 330. Well, then of course, it's going to divide about that. If you know the length of the wire, you know what I mean? There is no ground. And what manufacturers' surge protection device will do is they say, well, you know, we guarantee protection and like that. And they say, well, you know, we came out to your house and we measured your ground and you got a bad ground and surge protection. But watch this, Jacob. A lot of people, I would say almost everybody thinks that a ground has an effect on the performance of a surge protection device. But it doesn't at all. Zero, nada. So what they try to do is say, well, we checked your ground. Look, you see this loose connection here on your ground? Well, there's your problem. No, the problem is that the product is not designed properly. So John, talk to us about that.
Yeah, so there are, I mean, it's like any product, there's good and bad. Most of them are good, but there are some that have design issues and manufacturing issues. One of the problems that we see with surge protection devices are due to a device called an MOV, and that's a solid state component that's actually doing the conducting when the voltage exceeds a certain value. So in this case, in the case we have on the graphic, if the voltage gets above 330 volts or so, it starts conducting. And like I said earlier, it's a discrete device. It can only handle a certain amount of current. So if you exceed the rating of the device, it's going to get real hot, and it can actually catastrophically fail. It can ignite. MOVs are also susceptible to thermal runaway. They can. There's a whole host of issues that can go wrong with MOVs, and that's a well-known problem. So the key for the manufacturers is to design in a way to manage the heat when the MOV does enter into a thermal runaway situation.
What causes a thermal runaway?
Manufacturing anomalies can cause a thermal runaway. Repetitive overvoltage can cause a thermal runaway.
Strike. Or other transients.
Right. They can't operate indefinitely. And a lot of times, consecutive and repetitive overvoltages will decrease the clamping voltage of an MOV. So if it starts out as a 330 volt device and it sees 10 overvoltages of a certain magnitude or a certain value, now it may be a 320 volt device, and it sees a few more. Now it might be a 300 volt device. And so you start getting to the point where at the positive and negative half of every cycle on the sine wave, you start conducting. So at every single cycle, you're conducting a little bit, and then it'll decrease the clamping voltage even more. Now a little bit more at the positive half of every cycle, and the negative half of every cycle, you're conducting a little bit. And that's usually what causes the thermal runaway.
Now.
Yeah.
You keep getting below the waveform. And then
And now there's no overvoltage, but it's continuously conducting current. It's going to get hotter and hotter, and there's a little polymer coating on it that'll ignite. And if you don't manage that heat can cause issues, especially for the SPDs that have plastic enclosures. The plastic enclosure is not supposed to ignite, but in some cases, through manufacturing anomalies and manufacturing defects, it can.
I've seen that happen at my personal properties, where I go out there and I'm looking at this thing and I see what was the surge protector and there's nothing there, and it's all, part of its plastic is there and it's all black, and I look on the ground and all this stuff is on the ground and grass is caught on fire then. And of course, fortunately it was outside, you know what I mean? But it could have been inside of a building.
Right, yeah, and we've investigated some of those that have been inside or mounted to the side of a house with vinyl siding, and you ignite the SPD and you ignite the siding of the house, and then you've got a significant house fire.
All right, let's go into 242.12b. Jacob, there are different types of surge protection devices. This is a type 1. A type 1 surge protection device is permitted to be installed what is called at the service. And that's an electrical term. That means it's the beginning part of the wiring coming to the building. It's right there. And then there's a type 2 that would be installed at, let's say, a panel, which is not at the main service. but it's at a panel. Can you visualize that? And then type 3 is a type that you'd put like on a receptacle. Now the purpose of surge protection devices is to protect the equipment. But sometimes, and not sometimes, I mean, you have energy coming in as substantial numbers, and it's going to come in on the utility secondary conductors. It's going to come in on the wires, and it's going to go back on the same wires. John, explain why we have a type 1, 2, and 3. What's the reason? Can I just put a type 3 in there and, just get a little strip and drop that in there? I mean, I'm trying to protect my expensive equipment that's trying to avoid Murphy,
Sure. Well, going back to the original graphic we were looking at earlier, where the magnitude or the value of the overvoltage was 6,000 volts over on the primary, and then 1,000 volts. If you drew that out more and expanded it, you've got a much bigger system. So the more times you can capture that or shunt that energy and cause a voltage drop upstream, the less the magnitude.
Jacob, let me explain what he is saying. Imagine that I put a surge protection device here, right? And this is 6,000, and I put a surge protection device here. I'd be able to create enough voltage drop to drop that voltage down, right? But then I put another, that's a type 1 at the surface. I put another surge protection device at the panel. Well, then that would be able to clamp that voltage down a little bit more. And then I put the last surge protection device at the load. So maybe I'm going to clamp this down to, let's say this was 5,000 volts. I clamp it down to 3,000. Then the one at the panel, I'm going to clamp it down to, let's say, 2,000. And then the one at the load, I'm going to clamp it down to 330. So therefore, you're not using all that energy into one little guy at the outlet. Like you said, well, it's only going to last so long as it keeps hitting. But if you can get one at the surface that has more MOVs and a bigger but cut it down, and then get less MOVs, a little smaller, and then you keep going. And by the time you get to the low, so the goal is that it's not required to put these in, but if you want to save electronic equipment from transients and lightning strikes or lightning events from the primary side, then you might want to put more. Eric?
Well, there's another difference. And it has to do with where the surge protection is installed. If it is installed in between the transformer and your main, it has to be a type 1. A type 2 can only be installed on the downstream side of overcurrent protection.
So you have type 1 that can be installed between the utility and the main, because they realize this thing is going to have high energy. I mean, remember the available short circuit current we talked about? It comes in at 46. It starts at 46,000 and it goes to 34,000 and 16. Well, then the type 1, which is really close to the beginning, it needs to be recognizing that there's going to be a lot of energy from the fault beside the energy from the overvoltage. And then that's type 1. Type 2 is, you put it in the panel, but type 2 has a breaker protecting it. If you take a look at the graphic here, type 1 right here, actually type 1 doesn't have to have overcurrent protection, but it could require overcurrent protection. Type 2 would require overcurrent protection, and type 3 is the little tiny small baby things to kind of protect it. Yes?
No matter, I think it's important to point out also, no matter where you install it, the current is still not going through the ground. Even a type 1, the principle is the same as we described. It's just a different part of the premises wiring or the utility system.
So we'll have to do a better job, and that is to show type 1, show it clamping, type 2, clamping, and then type 3, at the load clamping. And the last comment, talk to us about the length of the conductors. Oh, Brian, you're going to say something?
Well, I was just going to say, obviously being a contractor in Florida, we've been installing surge for ever, literally since I opened my business. And almost every manufacturer actually recommends having at least 2 to all 3 of the types installed in a system that's a critical system. So we did a lot of work in medical, we did a lot of work in computer areas, and I think one of the simplest explanations that I ever heard, and it was not technical, was that it's kind of like peeling an onion, that each of the surge, and he said actually recommended in every panel sometimes, depending on the system design, you're actually just peeling another layer of current off so that every surge protector in the system is able to do its job a little bit better downstream from that device.
Well, you're able to create more current, more voltage drop each stream to get that the voltage down. And the last thing is routing of the conductors. 242.24 says surge protection to conductors must not be any longer than necessary, and unnecessary bends must be avoided. What's the deal there?
Sure. So two things. The main thing, you don't want the voltage drop that is occurring because of the surge protection device to be all across the leads of the surge protection device, because then you're not affecting the load. You're not really accomplishing anything. So the shorter the leads, the better. And you don't want them to make any unnecessary bends, just because a lot of these transients are very fast transients. You want to minimize the impedance or the resistance between the surge protection device and the panel board bus or the service conductors.
All right, let me do a final closing here. Surge protection devices are designed to shunt the circuit in a way that it creates a high current circuit, and that's going to drop the voltage down, and it's unrelated in any way with the equipment grounding conductor, and it's not related in any way with the ground of the surface of a building. Now, we have seen, and I had a conversation with Tom, Tom's not here, he had to leave today, that apparently some surge protection devices have shunt things to the ground, instead of phase to phase or phase to neutral. And what happened was it ended up raising the voltage of the ground and affecting some GFCIs and AFCIs.
To the equipment ground. He was
To the
referring to the equipment ground.
Yeah, to the equipment ground
in a
conductor.
type 3.
In a type 3. All right, listen, hopefully that gives you an insight. You do not need an equipment grounding conductor. Sorry about that. And you do not need the ground in any way to performance. But some manufacturers do provide surge protection that'll go line to line to neutral, and also line to ground. And I talked to a guy who knows surge protection. I'm like, you know that you don't go to ground for any reason. Why did you do that? He goes, well, our competitors do. And because our competitors had it lined to ground in their advertising, then people were saying, well, those guys don't even know what they're doing because they're not doing line to ground. So we had to put surge protection added in there for line to ground, just so that we would not be beat up by saying that we don't provide the protection that the other people provide. So hope that helps you. God bless.